Hello, this is Mr. Boston, and we're going to try another energy conservation problem here. So we have a gentleman named Tarzan. He wants to swing over a very deadly moat of crocodiles for some reason. And here's the problem. Tarzan swings on a vine as shown in the diagram at right. If his initial speed when swinging was 2.5 meters per second, then can he reach the other side of the ravine? The vine is 6 meters long, L, as shown in the diagram. He leaves the edge and needs to reach the other side of the ravine with a vine and at the angle of 35 degrees for theta, as shown here. All right. So this is an interesting question in that they don't tell us how to solve by virtue of the question. It's an open-ended question. They just ask, can he reach the other side? And we got to figure out how to answer that question. So this is very interesting. So what I always like to do first is to start by labeling what facts we have to work with. So his initial speed, this is VO, is right here. We're given the length L, and here's our angle. Man, not a whole lot to work with, and we don't even know what we're supposed to like solve for really here. So, all right, kind of a vague start here. So let's think about this. So I think a natural idea here would be to say, well, maybe we're going to consider his energy right here compared to what energy he'd need to get right here. Okay, and let's just talk about those energy transformations here real quick, and let's consider another point right here. Okay, so I like to consider the lowest point in my problem as the zero height. So I'm going to measure everything up from this position. This is his lowest height. And so this is going to be some height h that he reaches. And we're going to have, basically I don't have any springs or thermal energy stuff, so I'm going to have some initial kinetic energy here. I'm still going to have some kinetic energy here, but I'm going to have a little bit of UG at this point. And up here, I might have still some kinetic energy and definitely some more UG. And we don't know exactly how he's going to reach the top, but does he just barely reach there so that his velocity is 0 at that moment, and or is he going to actually swing past it with some speed still? We don't know. It's open-ended. So this is the energy transformations we have around here. All right, so I see that I have him, and I'm going to include Tarzan as my system. And I see we're going to have changes of height. So I'm going to say we're going to include the Earth in our system. And I see when he's swinging, he's going to have a contact force here, an external force, tension pulling on him, but he doesn't ever displace along that tension direction. Okay, so we're going to say this is isolated. Whatever kinetic energy he has initially is going to be the kinetic energy, it's going to be the final energy he has at this point. The vine isn't like giving him any energy. So I'm going to say isolated. Just by virtue of grabbing onto the vine, it doesn't give him energy. Okay, so I think we have an idea here about our energy transformations. Maybe well, it's a little bit vague. At this point, I would just say try anything. A lot of times physics students say, Mr. Boston, I don't know how to start. Well, try an energy conservation of some type. We suspect he's going to have kinetic energy here, and we're going to have some kind of combination of kinetic and potential here. So let's try that and see what happens. So how our energy conservation equation says, how do we get to our final energy states? Well, that depends on how you started, plus how you're trying to change what was happening for your system. And so we're saying this is an isolated system, so we don't have any work. Therefore, our final energy is going to be equal to our initial energy. And we think we have some kinetic energy initial. And that's going to turn into, we think, some UG, some gravitational potential energy, plus some final kinetic, perhaps. Okay, and we're going to plug in our details for all these energies. Kinetic energy is 1/2 mv initial squared. I think that's going to turn into some mgh plus some 1/2 mv final squared. So let's go ahead and put in our details. Before we do that, though, I noticed something about my m's here. It's in every term, so mathematically we can cancel that out. What that means physically is that if a grown man ran and jumped off this vine at a certain speed, and that is more massive, and then a small child ran and jumped off this vine at the exact same speed, they would actually swing up to the same height. The mass would have no effect. So if I'm able to get a certain amount of mass up to a certain speed, then that same mass is going to end up reaching a certain height at a certain speed. And so basically, how high I go only depends upon how fast I go off at the bottom here. Okay, so we can go ahead and maybe put in the facts of the matter here. So I have 1/2. We are, and boy, that's interesting, is that mass, because they never actually told us, and that's why they didn't have to tell us. Anyways, so our initial speed was 2.5 squared. That's going to be equal to 9.8. We have h, I'm just going to say, the 1/2 of our final velocity. And they never directly tell us what the h is, so I think I need to do a little bit of a side work here for h. So let's just do some side work here for h. So h, what's h all about? Okay, so our vine looks like this. When we first jump on it, when Tarzan first jumps on it, it's right here. Then it swings up some angle theta to the top position, perhaps. And so that's how that looks. Now, we need to figure out, we're actually told the length of this vine and the angle. So let's go ahead and put in some of those facts and see kind of what that gives us here. So if we know this length and the angle, then I think we're going to have situation where that kind of makes a nice right triangle for us. And we know that this is 6 meters, and we know that this is 35 degrees right here. And so I think we could solve for this adjacent side, and we know that this length right here is going to be still 6. This vine's 6 over here, and it's also 6 over here. And I think we can find our height right here. Let me just show you how you do that. So a lot of times in physics, we need another relationship to be able to solve. And a lot of times we just end up adding line segments. So let me show you what I mean here. So I think we could say this length L along the side here is equal to the adjacent side of this little triangle, A, plus H. From there we can say, well, H is just going to be equal to L minus A. So let's go solve for that adjacent side here real quick. So in this triangle, I think I have an adjacent and a hypotenuse and angle, so I can say cosine of 35 degrees is going to equal to my adjacent over my hypotenuse, which we know is 6. Therefore, we can say A is equal to 6 cosine of 35, which is equal to 4.9 meters. So we can come back up into this thing and say, hey, we know some stuff about this. L is 6. Subtract 4.9 from it, and we get 1.1 meters for my h. So the total length is 6. We figured out that this was 4.9. So 6 minus 4.9 should equal our height that we'd have to get up to this spot. So now we can put in to this spot 4.9. Let me go ahead and do this. Oh, sorry, no. In this spot we can put in it must be a 1.1 change in height to go up this far then. Okay. So this is a vague question. Do we make it to the other side? Well, let's think about this for a second. Let's think about how we could maybe answer this. So if we say our initial kinetic energy right here is less than the potential energy needed to get to here, then there's no way we can make it up to that height, let alone have some speed left over. So if we want to make it up to here, we got to have enough kinetic energy to match the potential energy needed to get here. So if our kinetic energy initial is less, then we miss. There's one outcome we could have. Okay, another outcome we could have is what if our kinetic energy initial is equal to UG? Then that would be a make. We actually do have enough kinetic energy to make it up there, but it would be barely. So by the time we swing there, we're actually at the very top, so we actually come to a stop and we let go, and it's just the perfect make. And then what if our kinetic energy initial was greater than UG that we need right here? Well, then we'd have some leftover kinetic energy. And so we would make it, but it would be an easy make. We'd even have some extra energy left over, and we might swing up and fly forward a little bit right there. Okay, so basically we need to check this. What side of this boundary is it on? Are we less than UG, or are we actually able to have the same amount? And so what I maybe recommend doing right here is let's check out these numbers. So this is our kinetic initial term right here, and here is our UG. And let's see what those numbers are. So when we plug in to see what this term is compared to this term, I plug in 1/2 2.5 squared, and I get 3.1 right here. Okay, we're curious how it will compare with this term, the UG term right here. Okay, and so when I plug in 9.8 times 1.1, I get 10.8. And 10.8 is much greater than 3.1. Therefore, we are in this situation, and we don't even have to worry about solving for our final velocity. We know we don't even have enough kinetic energy to make this. So our answer is it's a miss. Okay, and if you did plug into your calculator and try to solve for this, you get the square root of a negative number, and so this has V is equal to null, or no solutions. Okay, and that means nope, we don't have enough energy to make it. Okay, so an open-ended question. We saw that we had some energy transformations there. We weren't exactly sure what, but we decided to be brave and go ahead and do an energy conservation approach. And eventually we came to the conclusion that we could basically just compare our initial kinetic energy to maybe our potential energy and see if we had enough to get there. And we saw that indeed we did not. Okay, and so I want to just take a moment here. And by the way, we had to do a little bit of geometry, which was the most annoying part of this, with how our vine swings around, and that was we had to be careful about that. But uh, hopefully that gives you a good idea how to approach a problem like this, an open-ended problem for energy transformations. And I would like to just do energy bar chart real quick. And it's not going to be actually energy because we cancel out the mass, but you'll get the idea here. So let me just set that up here. Okay, so we saw we had this kind of thing going on here. So basically, I labeled this with 5 and 10. And this isn't exactly energy because we cancel out the mass thing, but this will give us an idea. We got basically our initial kinetic energy was 3. Okay, we didn't have any initial potential energy. We had no springs involved here. We didn't have any friction involved. And so we're wondering, and we didn't have any work, but we're wondering what we had. With this stuff, we had enough energy to get over there. And we saw that our initial potential energy had to be up here around, oops, up here around 10.8. And boy, we didn't have enough initial kinetic energy to even get close to that. So we can maybe say, no, this is not equal. So that was no solution for this case. So maybe there's a little visualization to help you along with what our solution means. All right, thank you for watching.